Okay, let's get started. If you have a quiz 10 to turn in, there's a pile right here. If you haven't picked up your midterm, they're up here too. If you haven't picked up your quiz 9, lab 5, I don't have homework 3s done yet. They're up here also, so feel free to pick those up. So midterms were actually really good. I was really happy with your midterm scores. So whenever I teach this class, the average is around 60% average for a midterm. And this one was, let's see if I can do this right. It would be like an 85. So I was extremely happy to see the average be so high. So the average number of points was in the high 120s. I don't remember the exact number, but it's in the high 120s. So that was really, really good. So I think it'd be a good idea to just go through the sample solutions and then talk about it. One thing to keep in mind is I'm a human. So you might not think I'm a human, but in fact I am. So I actually do make mistakes, believe it or not. So because of that, I may have added up your points wrong, although that's probably not true because I used a calculator. Although I could have inputted it wrong. I could have given you not enough points that you deserve on a question. So, and the whole sorts of other things that could happen. So if I didn't add up the points right, or I didn't transfer the points right to the front page, then just bring it to me, tell me, Ryan, you screwed up, please fix my test, then I can help you there. But if it's something like, I think I deserve more points on this question because X, Y, and Z, what you need to do is to write the things that you feel like you have missed points on, what questions they are, and what the reason is. Then what will happen is you'll give it to me. I will regrade the entire test, not just that one question, but the entire thing, because I may have screwed up another question. And whatever the score is that is a result of that, whether it's lower, the same, or higher, that is the final score. Okay? So just be absolutely sure that you know that you deserve more points on that question before you do that, because your score might go down. Okay, so let's just go over the sample solutions. So the first question many people got totally right or very close to right. So part A, I think everyone got, unless I'm mistaken. If you didn't get all the points, you got most of them. The second one, everyone did well also, so that was really good. So part C is where people missed some points. A lot of people applied the product construction, which is good. One thing that some people didn't keep in mind was that I have the complement of L2 here, whereas some people just worked with the original L2, so you missed a few points there. Another thing that some people did was to make the DFA directly and not use the product construction, which is also fine because it doesn't say you have to use the product construction, but it's just another way that you can do it. Any questions on question 1? Okay, question 2. Some people for part A just didn't follow the method exactly. So when I say that you have to use the methods in class, you have to use the methods in class. So some people missed points for this one because they didn't use the methods. And one thing to keep in mind for this question is that the epsilon transition that goes back to Q0, it doesn't have to go to Q0, it can go to Q1 instead. Because it turns out there's no difference between what the language is, whether you go to the new start state or the original one. The part B is just converting it to a DFA just by using the power set construction. And I didn't want you to use every single subset of the states, just do the build your states as you go method, the way that we have learned to do it. So the epsilon closure of Q0 is Q0, Q1, Q2, Q3, and then you work from there. Just by seeing where you go on 1, where you go on 0, and just keep going. Any questions on Q2? Okay, Q3, a lot of people missed a lot of points, and this is the most concerning question of the whole bunch, I think. So whenever I bold instructions, I think that's what I mean to be very important. So when I bolded these and capitalized things, that's what I want you to pay attention to. So if you're writing like a whole page of things for each of these, you're working way too hard. So if it says brief, be brief. So for the first one, all you needed to say was that regular languages are closed under intersection and complement. You could have said in it because of the product construction and how we did it with DFAs by flipping final and non-final states. Ooh, that's a typo. So this shouldn't be A union B, it should be A intersection B. That's just a typo on my part. For question B and C, you only have to provide one counterexample. So just by saying, this is not true in general, or that it's the same string twice, so therefore it cannot possibly be the same language as picking any string. Well, that's not true, because if you pick A to be the empty set, then these two are the same. Because if you concatenate the empty set with the empty set, you still get the empty set, and the thing on the right-hand side is also the empty set, so they're the same. So it's not true in general because you can find a counterexample for it. So that's why a lot of people missed part B and C, is that if the statement's false, just give a counterexample. You don't need to reason about like what it means in the general case. Just give a single counterexample to show why it's false. And I have one here, but and of course there are many other examples other than this, but it's just one example. And then, so pretty much everyone, I think some people missed whether this was false or true. Again, for the same reason, a lot of people missed points because they said it's false, which is good, but the problem is that they didn't give a counterexample or have good enough reasoning to show that there is a counterexample. So here I just give a counterexample. Just let A be any non-regular language and B its complement, then their intersection's empty, and A is not regular, and we also know B is not regular, but that's not important here. So some other examples were if you pick A to be the same thing and then B to be the empty set, then that also works. So, but because then you can just show that, well, A is not regular, so therefore you get the contradiction. Any questions on Q3? Okay, Q4, there was a big gap in reasoning for quite a few of you for this one. So a lot of you did write that it's just the reverse language, which is good. It's just a matter of showing it or proving that you get the right, you really do get the right language. Because you can just say that you reverse the right-hand sides of all the roles, which is what it is, essentially, but it's proving or showing that you get the reverse language. So you can just apply that operation to any regular grammar, but it not necessarily, until you prove it, means that you get the reverse language. And so how do you prove this? Well, if you derive the string in a certain way, well, because it's a regular grammar, you have a bunch of terminals in what you've derived so far with a variable at the end. And then if you do the same kind of derivation in the reversed grammar, well, you have the terminals going the other way with the variable at the front, which means that you're going to be deriving the string backwards, which is what the reverse language is. So I made it a little more formal here, and you don't have to be this formal, but it's just that you need to be able to write in a formal way. Any questions on Q4? Q5, almost everyone did either perfect or very close. So question 5, yeah, it was just showing it's not regular. There are some people who didn't pick a string that's in the language and length at least p. So that's the number one thing that you should be doing every single time you do your pumping lemma proof. You have to pick a string that's in the language and of length at least p. A string that several people picked was a to the p plus 1, b to the p, c to the p, which is in the language and long enough, so that's good. But then they picked beta equals 0, which you could do. Well, the resulting string that you get out of it is, actually I'm going to modify it. I'm going to be a to the p plus 1, b to the p plus 1. So then if I pick beta equals 0, well, the length of the string is, so the string is a to the p plus 1 minus beta, b to the p plus 1, c to the p. And they said, well, beta prevents this from being an almost draw now, because you're subtracting and then now you get a contradiction. Is that true here? Right. Well, beta has to be... What do we know about beta in general? It's at least 1. Well, could it be equal to 1? Yeah. What if it is equal to 1? Well, if it's equal to 1, how many A's do I have? P of them. So do I still have an almost draw? Yeah. So there is a choice of I that I can, this choice of I that I picked, actually no, that's not beta equals 0. That's my mistake. Choosing I equals 0. Sorry. Yeah, I was getting ahead of myself. I equals 0 means I remove the occurrence of y, which means I get a minus beta here. But I still have an almost draw, but I want to get out of the language. So a better choice would have been to pick, in this particular case, to pick I equal 2. Because then you'll get a p plus 1 plus beta, which means you have at least p plus 2 A's. And so the difference between the max and the min is 2, which is not an almost draw. Any questions about this one? Yeah.
So instead if we pick a to the p, b to the p plus 1, then c to the p, and then we pick I equal to 0.
Yeah. So if you instead picked a to the p, b to the p plus 1, c to, I think this is what you said, right? Yeah. So then if we picked I equals 0, then what we'll have is a to the p minus beta, b to the p plus 1, c to the p. And because beta is at least 1, the difference between the max and the min is at least 2. And so therefore you could leave the language. Yeah. So the choice of I is pretty heavily dependent on what the original string you picked is. So in one case we have 0 not working, in the other case we do. So just be sure you know what you're doing and what string you're picking. Any questions otherwise about this? As I said, this was actually much better than I've ever seen it done, which is amazing. For the last question, not many people attempted it, but the basic idea is very similar to the pumping lemma that we proved. If there are p states in the DFA, then for any p-length substring in there, because there are only p states, you'll have a repetition among them because of the pigeonhole principle. It's the same argument as the pumping lemma that we had before. So this is just really asking you, do you understand how the pumping lemma proof works? Why it's true? It's because you can pump any p-length segment in the entire string. Okay? Any questions about this or the rest of the test? Okay, so let's continue where we left off. So I want to talk about several things that can go that can happen in a grammar. So what is one aspect of a context-free grammar that we have explored but we don't really like? What is something that would not be useful if we tried to use it in a parser or a compiler of some kind?
Ambiguous.
Yeah, so ambiguity is a huge issue. Right? We don't like ambiguity. We want things to be precise and have one way of deriving things. But if there was such a way to eliminate ambiguity from a context-free grammar, that would be super. Because if there was some procedure, like from the NFA to DFA idea, but from an ambiguous context-free grammar to an equivalent one that is not ambiguous, then that would be really cool. But unfortunately, it is not possible to always remove ambiguity, sadly. So there are languages that are called, and you don't need to know this for a test or anything, but there are languages called inherently ambiguous, which means that every single grammar for them is ambiguous. So there doesn't even exist an unambiguous grammar for it. So unfortunately, it's just not possible to do in the general case. But what if we were able to try to remove some of the ambiguity? Maybe not all of it, but at least some of it. So what can we do? So how can we remove as much ambiguity as possible? And ambiguity can come up in a number of ways. So one thing that could happen is we can just have normal ambiguity, which means that, let's just say we have this silly grammar. So S goes to epsilon or S. So how many ways can we derive the empty string in this grammar? Yeah, infinitely many, right? That's kind of annoying. So what about this one, though? So this is obviously a silly example, but what if you have something like this? So we're eliminating that problem. A goes to B, B goes to C, C goes to D, D goes to epsilon. And you may say, well, that's kind of silly, right? But it's perfectly allowable within the definition of a context-free grammar, so we're allowed to do that. And in fact, it's a regular grammar too, so it's definitely allowable. So how many ways can we derive the empty string here? Yeah, 2 ways. We can do it to, we're assuming that S is the start variable. S goes to empty, or we can go down the long chain of those rules to hit the bottom. So if there was such a way that we could try to enforce what the grammar looked like and try to remove as much ambiguity as possible, that'd be nice. So we actually talked about this before in the last lab. Sorry to give the spoiler away, but we're going to actually talk about it now. So a context-free grammar is in Chomsky normal form if every rule is of the form, and we have three cases. Either S goes to epsilon, a variable goes to a terminal, or a variable goes to two non-start variables. So just as a reminder, A is a variable, little a is a terminal. So we're saying that a grammar is in Chomsky normal form if every single rule is one of those three types. So it's kind of like a regular grammar, almost, not quite, but it's there. There's a certain set of rule types you're allowed to have, and if you have any rule that does not conform to one of those three, it is not in Chomsky normal form. But if every rule is, then it is in Chomsky normal form. And we're going to call this CNF. I know there are a lot of three-letter acronyms. Yeah.
Do B and C have to be different?
What's that?
Do B and C have to be different?
No. They don't have to be different, but they cannot be the start variable. That's the only case. Yeah.
So C can't be the start variable, but can there be a place where you can do a declaration from C? So like if we get another variable from say like D to C, and then or S.
So what's your example?
Like, is it possible that there could be a deliberation that could force C to equal S?
No. Because think about what happens. So either S goes to empty or S goes to a terminal, which means that you stop anyway. But then if you go to the other two, if you have S go to two variables, well, neither of them are the start variable, right? But then all of the rules that correspond to those two variables cannot ever make the start variable. So in a sense, once you're in the start variable and then you go to another variable, you cannot escape it. So you can't go back to the start variable. Well, you can never go back to the start variable, according to this. But it's basically there's only one way through. But there's something that's actually kind of interesting here. Which variable can make the empty string? S, right? Can any other make this? No, because S does not appear on the right-hand side of any rule. So what does that even tell us further? If we apply a variable makes two variables, can either of those two variables make the empty string? No, so they must generate a character at least. So one thing that's kind of annoying about normal CFGs, unrestricted context-free grammars, is that you can have, say like in the balanced parentheses example, where we had a bunch of S's and all of them went to empty at some point. We had so many occurrences of the start variable. So we built this long string, and then we collapsed it back by removing the empty strings. Here, once you apply two variables, one of those rules, they must make something of the string. Yeah.
But what if you had them just infinitely pointing to more variables rather than terminals? Like, can you guarantee that they have to go to a terminal eventually? Because otherwise it wouldn't generate a string.
So we have to have a string in mind. So yeah, but that's also something to keep in mind. Well, think about what happens. So if each variable on this right-hand side makes something, then if we have n characters to make, if I have more than n variables, then I can't make that string. So we can actually figure out, and you may do this in the lab, I think, to figure out exactly how many rule applications that you will always take, no matter what. So no matter what the string is, you know exactly how many rules to apply. Whereas in a normal grammar, Say like the example on the right, we don't know how many to do in general. Whereas in a context-free, with a grammar in CNF, we know exactly how many. Isn't that pretty interesting? But the question you may you might have is, well, is CNF really special? Is it something that only some context-free grammars have, and that there are some languages that there's no grammar in CNF for them? Could it be possible that I can design a language that has no context-free grammar in CNF? So one of the amazing things that we'll prove, maybe not totally today, but most of it today, is that every grammar can be converted into one that is in CNF. Every one. Yeah.
What if you have just one, like a language of just one, a length of one character?
Mm-hmm.
You can't do that for this.
You sure? Yeah. So it's yeah. So we'll do. You mean? I think I know what you're asking, which is.
No, I was just making sure.
No. I'm actually pretty sure I know what you're asking, which is there's one variable on the right side.
No, I was
Okay.
just getting tricked.
Okay.
Thinking that you had to go straight to the VC and then you had to do two terminals, but you can just make S go to the character.
Okay. Any other questions? Okay, so let's actually look at a particular example of a grammar. So I'm just going to make up a grammar. There's no particular choice about what this grammar looks like. Okay. I have no idea what the language of this grammar is, but I just made it up. Okay. So is this grammar in CNF? No, and how can you tell? Yeah, there's a lot going wrong. So, and also one thing, what is the start variable? Can B be the start variable? Just because we called it S before, does it mean it has to be called S every time? No. So any variable could be the start variable. Even if it doesn't make sense, it could be the start variable. But let's call it S this time. So let's just say that S is the start variable. And then now we can start thinking about what to do. So, well, one of the things that we kind of see is that there's an S on the right side of these rules. So is there a way that we can modify this grammar so that's not the case? That there's no S on the right-hand side? Or no start variable on the right-hand side? Yeah, what could we do?
Like instead of A going to S, we can say A goes to A, B, or
That is true. We could just copy the rules down, but that's going to be addressing a problem that we're going to see later. I'm only focused on S appearing at all on the right side. Whether it includes another terminal or another variable with it, it's just I'm concerned that S appears on the right-hand side right now. We'll address that at a point, though. Yeah.
Megan, you asked that goes to C and then call all those S's C now.
So you're saying S goes to C, and then what's C you have?
And then C will go to A, B, or like C will have the same rule as that start variable there.
Okay, so it's basically take this entire big boy and then convert the S's to C's. Yeah, so that's actually exactly the right idea, but I'm going to modify it so that I don't touch this grammar as much as I can. So I'm going to introduce a new start variable into the grammar. So the first step here, there's going to be 5 steps, is to ensure start variable not on right-hand side of any rule. So what I'm going to do is I'm going to copy this grammar down. Maybe move it down a little more because I'm going to add stuff above it. Use a different color. So what I'm going to do here is I'm going to make a brand new start variable, which I'm going to call S0. So S0 is the new start variable. And what I'm going to do, which is based on the suggestion, is it's going to go to S directly. And that's all I'm going to do. So one thing that we should keep in mind as we're doing these is, well, if I want to claim that every single context-free grammar can be converted into CNF, well, I better be sure that at each step along the way, we don't change the language of the grammar. So if you could derive a string in the grammar before, can I derive a string now? And vice versa. So if I could derive a string in the old grammar up here, could I derive a string down here? So like if I started with S up there and applied a bunch of rules to get something, could I do this, a similar thing down here? Yeah, what would change though?
The only thing that changes is that you start at S0.
Right, you start at S0, you go to S, and then do exactly the same thing, because none of the other rules changed. No variables deleted, added, other than S0. But if I derive a string down here, could I derive the same string up there? And I claim yes, because every derivation in the bottom grammar has to start with what? S0 goes to S. Why? Because there's only one rule with S0. Yeah.
Maybe we'll address this like in a further step, but if we're trying to do CNF, shouldn't it have to go to like SS or something like that? Yeah,
we will address it in a later step. Okay. One thing that you should check at once we do all 5 steps is this order of the steps we're going to do is actually really important. So it's actually important that you do these steps in this order. And I actually invite you to figure out, well, what if we did it in a different order? Could it be possible that we don't get a grammar in CNF or we change the language in some way? So yeah, it's important that we do this one first. But we will address when we have exactly one variable on the right side. We will address that. Okay, any other questions? Yeah, so if you could derive a string down here, you can derive the same string up there, because down here, you start with S0 goes to S. Well, to get the string up there, you just chop off S0 goes to S at the front. So then you just start with S, and then you're all set. Any questions about that? Okay, so the next step is to deal, I should get rid of the circles because I don't need them. So the next step is to, and I'm going to put this in quotes because it's actually kind of important that it's in quotes, is to eliminate the epsilon rules. So why do you think I put eliminate in quotes there? What if I just said eliminate them, get rid of all of them?
Well, if we just eliminated them like with the obvious definition, we would probably change the grammar.
Yeah, you would change the language. We would change the grammar for sure, but we would change the language too, which is something we don't want to do. We don't want to change the strings that you can derive with the grammar. So, well, how do we eliminate? So A goes to epsilon, that's clearly not allowed. If I had S0 goes to epsilon, is that okay? The start variable goes to epsilon? Yeah, because that's one of the 3 types. But we can't have a non-start variable go to epsilon. That's definitely true. So, well, what could happen? Well, let's see. Well, we know that A can make the empty string, right? A can make the empty string because it's one of the rules. Could S make the empty string by itself? No, because both right-hand sides of it have some terminal associated with it. So S can't make the empty string. Can B make the empty string? Well, we determined that S can't make the empty string. So can B make the empty string? No, because the other rule associated with it makes a terminal. So, well, wait, what about S0 at the top? Can it make the empty string? No, because we had already established that S can't make the empty string, and so S0 can't either. So the only variable that can make the empty string is A, yeah.
Oh, wait, are you saying this particular?
Yeah, this particular grammar. Yeah. We'll deal with it in general, but in this particular grammar, only A can make the empty string. So we're going to introduce a new definition that tries to address this. So a variable is what is called nullable. Better give it a name. Unnamed variable. A variable A. I better not use A. Actually, yeah, N's a good choice. N is nullable. I'll do a new color for it. If one of 2 cases is true. So it's either the case that N makes the empty string directly, so then it's nullable, or the other case is N makes a bunch of variables, x1, x2, x3, xi, where all of x1 through xi are nullable. So the English interpretation of this is it's nullable if it can make the empty string in any way at all. So if it can make it directly, it's nullable. If it can make it indirectly through a bunch of other nullable variables, then it's nullable. So in our particular case, what is the only nullable variable? A, right. So what do we need to do? Well, suppose that a nullable variable is in some rule. So let me actually copy this grammar down. Down here. So let's look at this rule right here. So it's got variable A on the right-hand side, right? So the way to interpret this is, well, A could make something that is not the empty string. That's possible. Or it could make the empty string. So what if it did make the empty string? What would the right-hand side of that rule look like if A did make the empty string?
Just be AB.
Yeah, it would just be AB. So what are we going to do here? So what we're going to do is we're going to add rules corresponding to when a nullable variable is replaced with epsilon. And we'll see how to do it with this grammar. And in our particular case, we should make a list of the nullable variables, which in our case is just A, so that's actually kind of easy. So what we need to do in this grammar is add additional rules, never deleting rules yet. We're adding additional rules for when A, the variable, is replaced in that rule with epsilon. So S0 goes to S. Does that have the variable A in it? Nope. So we leave it alone. S goes to little b. That doesn't have the variable A in it, so you leave it alone. Actually, you leave them all alone, but it's just we're not dealing with it. S goes to variable A, little a, b. So does that have the variable A in it? Yep. So what we're going to do is we're going to add additional rules corresponding to when that variable is replaced with epsilon, which we've already figured out is little a, capital B. Does variable A appear anywhere else in the grammar? I mean, on the right-hand side, I mean. No. So, in fact, that's all we have to do. But suppose, just for sake of argument, this is pure, not for this grammar, just purely for sake of argument. So, suppose that we had A goes to A, capital A, B, capital A, C, capital A. So, how many rules would I have to add to this if each one of those A's on the right side could be replaced with epsilon independently? How many possibilities? 8 in total, yeah, so I would have to add 7. So just be sure that you're adding additional rules for every single choice of whether the variable stays in or drops out. That's my terminology. The variable either stays in or drops out. So in the one that we did before, we had the case of where the variable A stayed in, then we added a rule for when it dropped out. Okay, does that make sense? Yeah.
Do we have to delete the A list?
Yeah, exactly. So when we're done with all of this, then delete what I'm going to call unnecessary epsilon rules, which in our case means any epsilon rule not involving the start variable. So in this case, A goes to epsilon goes away. Okay? Any questions about that? Cool. So we're actually 2/5 of the way. And actually, these are this and the next step are the hardest ones. The last two are easy, comparatively. So I'm going to copy this down again. So is this grammar in CNF? Or is there something still wrong with it? Well, what's still wrong with it?
It's still not in the form where it's either variable going to terminal or variable
Right.
going to zero.
Yeah, there's still a lot wrong with it. The most notable, which I think is the fact that there's exactly one variable on the right-hand side for a lot of the rules. So S0 goes to S, that there's only one variable there. A goes to S, B goes to S. So what do you think we can do to avoid that problem? So I better introduce the terminology first. So the third step is to, again, quote, eliminate. And these rules where there's one variable on the right-hand side, those are called unit rules. So, yeah, I'll just write it. So a unit rule is a rule of the form A goes to a single variable and nothing else. And those are clearly not part of CNF. So how can we try to eliminate unit rules? What is something we can try? Yeah.
We try to maybe transition every unit rule into like a bigger rule.
And kinda, yeah. So think about like what S0 goes to S is doing. What is it really doing eventually? So S0 goes to S, then what is S going to do? It's going to apply one of its rules, right? So in effect, what is happening here is a unit rule is a long route to get to a variable where you can apply a real rule. It's just transitioning in some sense between a bunch of variables, in this case, through S. So if we wanted to get rid of those those unit rules, couldn't we try to shortcut our way there? In a sense, instead of going through S, couldn't we just say, let's just go straight to those rules directly? Well, I don't want to mess up the S rules, because those are good so far. So what I want to do is let's copy all of the rules of S up to S0 and shortcut our way to the rules that we're going to get to anyway. So that's what we're going to do here. So I'm going to get rid of the S right here, and I'm going to replace it with the entire right-hand side of S, all the rules of S. And actually, the exact same thing with A goes to S and B goes to S. So I'm going to first move this down so that, oops. So I'm going to copy this down. And then down at the bottom, well, the BBA rule I don't want to modify, so I'm going to leave it, but I'm going to get rid of the S and copy down the rules again. So for whatever rules that are there that are not unit rules, we don't touch them. But for the unit rules themselves, we get rid of the unit rule, and whatever variables on the right-hand side, we copy all of the other rules up to there, or down to there, whatever the case is. So you're just copying rules everywhere because now you're just shortcutting your way to that variable. And how do we know that? We should have checked this before. How do we know that we're not changing the language? Because we would have went through that variable anyway to get to those rules. So we're just shortcutting our way there. And before, all we're doing is we're simulating a rule with other rules, because we're just adding rules for one that we're trying to remove. So we're just simulating a rule with other ones. I think we're out of time, so I'll see you on Wednesday.